In this video, we are going to discuss the time domain analysis of first order RL and RC circuit. First of all, we will define the first order. So first order circuit means in the circuit there will be only one energy storing device, that is, it will contain a resistor and an inductor, or a resistor and a capacitor. And in the second order circuit we will find two energy storing device, that is RLC. Okay, so here first there will be two response when we discuss about time domain analysis of first order RL or RC circuit. So here the supply will be given a DC supply. So it is BS. This is the supply voltage. So first we will discuss the series RL circuit. So this is R, this is L, this is the switch, and this is the voltage source. Okay, so when we write this when we close this circuit at t equal to 0, at t equal to 0 minus, that is just before the closing of the circuit, there is no current is flowing. Okay, therefore IT will be equal to 0. So when we close this t equal to 0, when we close this switch at t equal to 0, a current will flow. Okay, this current will be considered as IT current will flow. So because of the connection of this inductor cannot change sudden change of the current. Okay, that's why at the time t equal to 0 also the current will be equal to IT will be equal to 0 only. Okay, then from this we can also say that the current will start to flow when at t is equal to 0 plus. Okay, so first of all, when we find out this response, there will be two types of response. Number one is force response. So force response will be available when there is a source in the circuit. Okay, so for this one circuit contain a source. Okay, and number two, we will get a natural response. So in this response we will get when no source in the circuit. Okay, for this circuit here source is the BS. Okay, BS is containing in this circuit when we close this switch at t equal to 0. So this response will be a force response. Okay, then we will apply KVL in the circuit and we will draw the equation. So the equation will be RIT plus L dit by dt equal to BS. Okay, so after rewriting it, we can write this equation as dit divided by dt plus R by L IT equal to Vs. Okay, so this equation can be compared with a equation like dy by dt plus alpha y equal to Q. So here we can see that this equation is nothing but it is a, and this equation is nothing but it is a non-homogeneous differential equation. Y equal to k e to the power minus alpha t plus e to the power minus alpha integration of q e to the power alpha t. Okay, it is given by this equation. So after comparing, we can write this equation of this equation 1. The solution can be written as it equal to k e to the power minus r by l t plus e to the power minus r by l t integration of bs by l e to the power r by l t dt. Okay, then we can solve it the equation to the power minus r by l t. So vs by l is a constant, then integrating it will get r by l t l by r. Okay, then this l will be cancelled out, and this e to the power minus r by l t and the e to the power r by l t, these two will also be cancelled out. Okay, then we can write bs by r plus k e to the power minus r by l t. Okay, then we can find out the value of k by applying initial condition, that is at t is equal to 0 it is equal to 0. Okay, so by applying this, 0 is equal to bs by r plus k e to the power minus r by l and multiply with 0. Okay, then we can write k is equal to minus bs by r. Okay, so after putting the value of k, we can write it equal to bs by r minus bs by r e to the power minus r by l t. Then we can again rewrite it as it is equal to bs by r 1 minus e to the power minus r l by t. Okay, then if we put a value known as tau equal to l by r in this equation, we can write it as bs by r 1 minus e to the power minus t by tau. Okay, so when we make this tau is equal to t, okay, then this equation can be written as it equal to bs by r 1 minus e to the power minus d by d. Okay, then we can write it is e to the power minus 1, so this is equal to bsr 1 minus 0.3688. Then it can be written as it equal to 0.632 bs by r. Okay, so the tau is the time taken when current is equal to 63.2% of the maximum value. Okay, and tau is known as time constant of the circuit. Okay, so if we draw the current versus time plot, so this is t and this is it, so this plot will be looks like this. Okay, maximum value will be bs by r. Okay, and this t equal to tau will be, this will be 63%. Okay, so here it is t is equal to tau and this is 0.632 bs by r. Okay, so this portion is before reaching the maximum value. Okay, this portion is known as the transient response. Okay, and after reaching the maximum value it will continue on maximum current only. Okay, and this portion is known as steady state value. Okay, so when we call this also a transient response of the RL circuit. Now we will find out the value of voltage drop at R and L. Okay, so first we will find out VR, that is voltage drop at the resistance. It is R IT, so it is R BS by R 1 minus e to the power minus R by LT. Okay, so this is equal to PS 1 minus e to the power R L by T. Okay, then we will find out BL, that is voltage drop at the inductor also. So this is L dit by dt, L d by dt, bs by r, 1 minus e to the power minus r by l t. So this is equal to L by r bs minus e to the power minus r by l t minus r by l is equal to this 2 will be cancelled out and this 2 will be cancelled out. Okay, then it will be bs e to the power minus rl by t. Okay, so when we draw this two plot, it will look like, okay, this is t, this is bl and br. Okay, so this two will look like this. So this value is ps, and here we can see that this is nothing but it is the plot of PR, and this is the plot of BL. Okay, then in the next case, first we consider a series RL circuit is connected to a voltage source BS. So this is PS, this is the switch, this is R, this is L. So this switch has one terminal and another is two terminal. Okay, so from one terminal at t is equal to 0, it bring to two terminal. Okay, so from here what we can see is t equal to 0 minus the current it will be equal to bs by r. Okay, then when we close this to the t is equal to 0, because of the inductor property, there won't be no sudden change in the current. Okay, that's why at t is equal to 0 also it will be equal to bs by r. Okay, because when the switch is at 1, the inductor behaves like a short circuit because the current is flowing for t is equal to infinity. Okay, now we will draw the circuit. So after t equal to 0, that is t equal to 0 plus, the circuit will look like this. Okay, so we'll consider this is the it. Okay, then we can draw this circuit as RIT plus L dit by dt equal to 0. So we can redraw it dit by dt r by L t equal to 0. Okay, so this can be compared with a differential equation like dy by dt plus alpha y equal to 0. So this equation is a homogeneous differential equation. Okay, and its solution is given by y equal to k to the power minus alpha t. Okay, then we can find the solution of this equation 2 also, comparing with this homogeneous differential equation. So we can write it equal to k e to the power minus r by L t. Okay, so the value of the k can be found out by applying initial condition, that is f t equal to 0, it is equal to ps by r. Therefore ps by r equal to k plus k equal to ps by r. Therefore we can write it is equal to bs by r e to the power minus r by rt. Okay, so this response is the natural response, and this response is the force response. Okay, so for this one we can draw the it versus t plot. Okay, so from here what we can see is this response is the decay response. Okay, and this response is the charging response of the RL circuit. Now we will find out this response for, now this S switch is closed at t equal to 0. Okay, at t equal to 0 this switch is closed, then the current flowing through this circuit is considered as IT. Applying K into L, RIT plus 1 by C equation of IT dt equal to bs. Okay, then differentiating with respect to t, we get r dit by dt plus 1 by c it equal to 0. Okay, so this is constant equal to 0. Okay, by rewriting it we can write dit by dt plus 1 by rc by t. So from the previous topic we already know that the solution of this will be equal to it will be equal to k e to the power minus 1 by rc t. Okay, so from here we can find out the value of k by applying initial condition that at t is equal to 0 the capacitor will behave like a short circuit. Okay, that's why it will be equal to bs by r. Okay, therefore bs by r is equal to k. Now we can write it equal to bs by r e to the power minus t by rc. Okay, if we draw this circuit response of it versus t, this is t, this is it. This plot will look like this. Okay, and this value is bs by r. Okay, now we can find out the voltage drop at r, that is vr equal to r it r. So it is bs by r e to the power minus t by rc. It is equal to vs e to the power minus t by rc. Then vc, that is voltage drop at the capacitor, is equal to 1 by c integration of it dt. So it is equal to 1 by c integration of bs by r e to the power minus t by rc dt. This is bs by rc e to the power minus t by rc minus rc plus k. Okay, k is the constant for integration. Then we can find out this rc can be cancelled out, so k minus bs e to the power minus RC. So at the initial condition, that is at t equal to 0, BC is also equal to 0. Okay, so 0 is equal to K minus BS. Then K is equal to BS. Therefore, BC is equal to BS 1 minus e to the power minus t by RC. So here, this can be again rewrite as BS 1 minus e to the power minus t by tau. Okay, so tau is the time period. So at where tau is equal to RC. Okay, so tau equal to t, BC is equal to BS 1 minus e to the power minus 1. So it's equal to 0.632 for BS. So from here, what we can say is tau, that is time constant, tau is the time taken when the capacitor is charged up to a 63.2% of BS. This is the supply voltage. Okay, so now we can draw the load. This is T and this is BC and over BR. So here capacitor is charging. Okay, this is BS and resistor is discharging. See, this is BC and this is BR. Again, if we consider a circuit where R and C is already connected across a voltage source BS. Okay, this is switch. So at t equal to 0, this switch 1 is connected to 2. Okay, then we can redraw this circuit as this is R, this is C. Now the discharge current will be in opposite direction to this is I prime T. It is in opposite direction to the charging current. Okay, now we can write the applying KVL. We can write the equation as BC. Okay, so here the charging voltage will be BC. Okay, so here a voltage of BC will be visible. Okay, BC plus R I prime T equal to 0. Okay, then BC plus RC D BC by dt. It is the discharge current. Discharge current. Okay, this is the discharge current. So after rewriting it, we can write dBc divided by dt plus 1 by RC BC equal to 0. So this is a homogeneous equation and its solution is BC is equal to K e to the power minus 1 by RCT. Okay, so at t is equal to 0, capacitor is already charged to BC, that is already charged to Vs. Okay, then at t equal to 0, BC is equal to Vs. Okay, and at t is equal to plus 0 plus also it will be equal to like this only. Okay, so from here we can write Bs is equal to T. Therefore Bc is equal to Bs e to the power minus T by RC. Okay, now we can find out the IT, that is the current, or also we can find out the voltage drop at R also. Okay, so now first we will find out I prime T. Okay, so I prime T is equal to C D BC by dt equal to C d by dt Bs e to the power minus T by RC. Okay, so this is GPS e to the power minus T by RC minus 1 by RC equal to now this CC will be cancelled out. Okay, so this will be equal to okay, this is the current. Then VR will be equal to R I prime T. Okay, it's equal to minus BS e to the power minus T by RC. Okay, so now we can draw the time versus voltage curve here. This is time, this is BC and VR. So here BC will be like this. This is BC. This is the plot for I prime T.